Hello guys, welcome back. This is lecture 18 of the lecture series Signals and Systems. In this video, we will be learning about the symmetry properties of discrete time Fourier series, and then we'll see about LTI systems using the properties of Fourier series, and then we'll look into filtering and examples of discrete time filters described by difference equation. So let's get started. So in the previous lecture, we saw about the discrete time Fourier series. So we had two equations. So first let us look at the analysis equation where we find a case from x of n. So summation n equal to n over n x of n e power minus j k 2 pi over n into n. This is the analysis equation. And then we had the synthesis equation where we represent x of n as linear combination of complex exponentials. So there we have summation k over n ak e power jk 2 pi over n into n. So this is our synthesis equation. And we also saw several properties of our discrete time Fourier series. Okay. So now we'll look at some symmetry properties as well. So first let us take a look at when x of n is real, right? So let us recall what we had in the previous lecture. So if x of n gives us Fourier series coefficient ak, then we know that our x conjugate of n gave us Fourier series coefficient a minus k conjugate, and x of minus n gave us the Fourier series coefficient a minus k. So if x of n is real, then what do we have? X of n equal to x conjugate of n, which means that your ak's are going to be equal to a minus k conjugate. So which means that your real part of ak is equal to your real part of a minus k, and your imaginary part of ak is equal to minus your imaginary part of a minus k, and your mod ak is equal to mod a minus k, and your face of ak is equal to minus face of a minus k. Okay. So then we can also see if x of n is even, then what we have? So you have x of minus n equal to x of n. So your a minus k is equal to ak, correct? So then if x of n is odd, what do we have? We have x of minus n equal to minus x of n, or a minus k equal to minus ak, or ak equal to minus a minus k. So now let us combine these two properties and see what happens. So if x of n is real and even, what happens? So for real, I have my a k equal to a minus k conjugate, and even I have ak equal to a minus k. So my ak is gonna be equal to ak conjugate. So which means that my ak's are also real and even, because this denotes even in ak, right? So this means that your ak's are also even, and this means that your ak's are odd. So if your x of n is real and odd, so let me write x of n here. So then what happens? For real, you have ak equal to a minus k star, and for odd you have AK equal to minus A minus K. So which means that your AK is going to be equal to minus AK conjugate, right? So your AKs are going to be purely imaginary and odd. Similarly, if you have X of n purely imaginary and even, then what you will have? So for purely imaginary, you will have AK equal to minus AK star, right? Because your X of n is equal to minus X conjugate of n. So for odd you have, even you have A minus K, this minus K. A minus K equal to AK. So this is going to be equal to AK equal to minus AK star. So your AKs are purely imaginary and even. Similarly, last one, your X of n are purely imaginary and odd. So purely imaginary, you have AK equal to minus A minus K star, and odd you have A minus K equal to minus AK. So overall you will get AK equal to AK star, correct? So this is similar to your AKs being real. So AKs are real and odd, okay? So then you also have even decomposition. So I can define a signal Xc of n such that it is even part of X of n, which is nothing but X of n plus X of minus n by 2, right? This is our even part of X of n. So if I take a Fourier series for this, X of n Fourier series nothing but AK, correct? Plus X of minus n, it will give me A minus K by 2. So this is my, let me call EK, coefficient, Fourier series coefficient of Xc of n. So if you consider E minus K, you can say that is also equal to EK, right? So EKs are even. So if we also consider X of n is real, then we also have A minus K equal to AK conjugate, right? Then your EK will be AK plus AK star by 2, which is nothing but real part of EK. So this is only true if X of n is real and its even part Fourier series will be given by real of AK. So similarly, your odd decomposition. So odd decomposition, what you have? XO of n equal to odd of X of n, which is nothing but X of n minus X of minus n by 2. So now the Fourier series of this will be AK minus A minus K by 2. And for this Fourier series, let me say it is called OK. So OK will be equal to this. So again, if you take O minus K, it is going to equal to A minus K minus AK by 2. So OKs are also odd, right? And if X of n is even, if X of n is real, then what we have? A minus K equal to AK conjugate, right? Then your OK becomes AK minus AK conjugate by 2, which is nothing but your, so by 2J will give me imaginary part, correct? So it will be j into imaginary part of ak. So these are the symmetry properties of Fourier series. Now let us look at the Fourier series and LTI systems. So that was our main goal, to simplify the analysis of LTI systems. So we already saw that when you pass a complex exponential through an LTI system with impulse response h of n, then you get an output given by some h of z into z power n, where your h of z is given by summation k equal to minus infinity to infinity h of k z power minus k, right? So this is true for any complex exponential. So we can just substitute j equal to e power j omega. And in this case, since we are considering periodic complex exponential, we can write k into 2 pi by n, which is nothing but k omega naught. K omega naught, which is equal to e power j k 2 pi over n. So then my h of e power j k omega naught will give me summation k equal to minus infinity to infinity h of k e power minus j k omega naught. Okay. Now I can write any signal x of n. Let's say this is the input signal, and it is periodic. Then I have the Fourier series representation. So summation k over n ak e power jk into 2 pi over n into n. So this is my Fourier series representation. And if I pass this x of n through my LTI system with impulse response h of n, then I should get some output. And this output should be nothing but, again, only the weight of the coefficients will change. All these exponential terms will actually appear as it is, because they are nothing but the eigenfunctions of the LTI system. So I'll get summation k over n ak h of e power jk omega naught e power jk 2 pi over n into n. And omega naught is nothing but 2 pi over n. Okay, so this is your outputs of your LTI system. And in general, you actually write it as h of e power j omega, since e power j omega is only the periodic part of z, right? You can write it as summation k equal to minus infinity to infinity h of k e power minus j omega k. Okay. And this is called as your frequency response of the system. Okay, because it is defining how the spectral components are changing, correct? So that's why it is called as the frequency response. Okay, so now let us take a look at an example. So let us say we have an input signal x of n equal to cos 2 pi n by n. And let's say our impulse response is given by h of n equal to alpha power n u of n. And alpha is between 1 and minus 1. So let us find our frequency response h of e power j omega, which is given by summation k equal to minus infinity to infinity h of k. H of k here is alpha power n u of n. So it is in terms of k. So I'll write k. And we have e power minus j omega k, right? So then what you will have? You will have k going from 0 to infinity, alpha power k e power minus j omega k, which is nothing but summation k equal to 0 to infinity, alpha e power minus j omega power k. So this is your infinite GP sum, right? And since your alpha is within less than 1, mod alpha is less than 1, this is going to converge. And it will converge to A by 1 minus R. So it will be A is 1 here, 1 by 1 minus alpha e power minus j omega. So this is my frequency response. What about my signal x of n in terms of complex exponentials? So I have cos 2 pi by n into n. So this I can write it as e power j 2 pi by n into n plus e power minus j 2 pi over n into n by 2. So you can observe that my coefficients are half here. E power j 2 pi n by n plus 1 by 2 e power minus j 2 pi over n into n. Now what will be my output y of n? So y of n will be nothing but it will be half into h of e power j 2 pi n by n e power j 2 pi n by n plus half into h of e power minus j 2 pi n by n e power minus j 2 pi by n into n. So I can substitute this e power j 2 pi n by n in here, right? Again, this n will not come, it will just be j into 2 pi over n. Only the omega naught matters, not the n, okay? So what will I get? I'll get 1 by 2 into 1 by 1 minus alpha e power minus j 2 pi over n, correct? E power j 2 pi n by n plus half into 1 by 1 minus alpha e power plus j here 2 pi over n e power minus j 2 pi by n into n. So if I write 1 by 1 minus alpha e power minus j 2 pi over n as some r into theta, right, r into e power j theta, then 1 by 1 minus alpha e power minus j plus j 2 pi over n will be nothing but r into e power minus j theta, correct? Assuming that alpha is real. When I take a conjugate, we get this. And r is also real, let's say. So then your y of n, I can write it as e power j into 2 pi over n plus theta plus e power minus j 2 pi over n minus, sorry, here it is plus theta again because you'll have minus divided by 2 and you'll also have an r term outside. So this is what you'll get, and if you simplify, you'll get r cos 2 pi over n into n plus theta. So you can see you've got a phase term and a magnitude term. And this was only possible because your AK was equal to A minus K star, which means that your h of n was real. So only then you were able to write this in the form of e power j theta and e power minus j theta, and was able to combine it finally into a cosine term. Okay, so cosine inputs give cosine outputs only if h of n is real. Otherwise, these will have a different coefficient and we may not be able to combine them. Okay, so this was our example. And another thing, if you note with this h of e power j omega, so let me again write it down. Summation k equal to minus infinity to infinity h of k e power minus j omega k, right? So it is actually periodic with periodicity 2 pi in omega. J omega plus 2 pi if I write. So this is nothing but minus infinity to infinity h of k e power minus j omega plus 2 pi k, right? And this is nothing but e power minus j k e power minus j 2 pi k, and this is going to be equal to 1. So then this is equal to my h of e power j omega. So h of e power j omega is periodic in omega with periodicity 2 pi. So now let us look at filtering. So in some cases, we would like to modify the spectral components of the signal, right? So in some cases, we would like to modify the amplitude of the spectral component. Of the signal, or maybe sometimes completely eliminate some of the components, right? Or completely eliminate some. So this action is referred to as filtering. So why this is important? Let's say we are sending, so you know that your h of e power j omega is gonna be periodic with period pi. So we'll consider, with period 2 pi. So we'll consider the region from minus pi to pi. Okay. So if it is something like this, it is going to repeat itself of every 2 pi. So it will be something like this, right? And even this side, minus 2 pi, it is going to repeat. Okay. So suppose I say I am only interested in the spectral components in this band, and these are all some added noises. Added noise and does not carry any information. So I will not want my original signal to be corrupted by noises. So what I will do, I'll put a filter. This, let me call it my signals. I'll call x of e power j omega, my signals frequency components. Then I'll put a filter, h of e power j omega. So I'll recover only that part. So pi, 2 pi, minus 2 pi, minus pi. Okay, I will keep my amplitude as 1. I can keep it as anything. So only the relative amplitude matters, right? So then my y of e power j omega will consist only of my desired components. Something like this. Right? So then on this I can do whatever I want, whatever I desire. So that is where these kind of filters are helpful. And this is a classic example of your low pass filter. So your discrete time low pass filter is given by this. So all your low frequency components are concentrated around omega equal to 0. And 0, 2 pi, minus 2 pi, all multiples of 2 pi. All these are low frequency components. And if you want high pass filter, all your high frequency components are going to be concentrated about minus pi. So why this is so? If you take e power j omega n, let's say, if it is 0, e power j 0 n, it is going to be constant. So it is, in the time domain, it is going to have a constant value, right? Of 1. Let's say this is x of n. Okay, for now let me take this out. So this is my low frequency signal or 0 frequency signal here. So DC signal, low frequency. So what is the highest frequency you can have in the discrete time domain? So you have 1, 1, 1 minus 1, again 1 minus 1. So this is the one which is rapidly changing. Anything less than this is not rapidly changing, right? So this is represented by e power j pi n, correct? So at one instant it is e power j pi, at the other instance it is e power minus j pi, and so on, which is given by minus 1 power n. So this will give your high frequency part. High frequency meaning it is rapidly changing. So this is the most rapidly changing signal you can get. So that is why all your high frequency components are concentrated around pi, and your low frequency components are concentrated around 0. So now we know how the high pass filter will look like. So omega 0 pi 2 pi minus pi minus 2 pi. So it should be something like this, correct? This will filter out all your high pass signal and suppress or make all the low pass signal 0. This is your high pass filter. And if you want to have a band pass filter, which is filtering some band of noise in between high and low, correct? So then you have minus pi, okay? Then you can have something like this. So this is going to filter out a band of frequencies. So here also you will have same. Here also around minus 3 pi you are going to have this kind of shape. 3 pi you will have this kind of shape. So this is your band pass filter. So now let us look at some examples. Of discrete time filters described by difference equations. Okay. So these low pass, high pass, band pass filter, you can see it is a strict rectangular kind of filter. So this is not possible to achieve in real life. So in real life, mostly you will have a smooth waveform only and not brick wall kind of filters. This is called as brick wall filter. In reality, you will observe something like this, okay? So let us look at an example of first order recursive discrete time filter. So I can take a difference equation representing this. Let me put alpha here. Then this is equal to x of n. So now if I take if I give an input to my system such that x of n is equal to e power j omega n, then my output y of n will be nothing but h of e power j omega n, right? So then what I will have? H of e power j omega n minus alpha into h of e power j omega. Since it is a time shift operation, I just need to multiply it with e power minus j omega n naught, right? Here n naught is 1 into e power j omega n. And my x of n is nothing but e power j omega n. So if I simplify, what will I get? My e power j omega n will cancel, and my h of e power j omega n into 1 minus alpha e power minus j omega is equal to 1. So my h of e power j omega is going to be equal to 1 by 1 minus alpha e power minus j omega. So this I can write it out as h of e power j omega is equal to 1 by 1 minus alpha cos j omega minus alpha sine j omega, right? So my magnitude of h of e power j omega is going to be 1 by root of 1 minus alpha cos, sorry, this is just omega. Here you will have j, right? So alpha cos omega whole square plus alpha square sine square omega under root. So if you plot this, you will get something like this. Omega pi minus pi 0. So at 0 it starts with 1 by 1 minus alpha, right? And at pi this again becomes 0, this becomes plus 1, so you will have 1 by 1 plus alpha, something like this, right? This has something like this. Similarly, your phase h of e power j omega will be minus tan inverse of minus alpha sine omega by 1 minus alpha cos omega. So this will be your phase. I am not plotting it now since it is a very complex function. But usually if you have a very simple expression, you can plot them. But what mostly matters is this amplitude or the magnitude information. You can see if alpha is less than 1, mod alpha less than 1, or let's say alpha only is less than 1, then you can see you have a boost around your low pass and some suppression around your high pass. So this acts like some kind of low pass function, right? So these kind of information you could have also got from your h of n. So the h of n for this is nothing but alpha power n u of n, right? So this will tell you how it is varying in the time domain. So if you have this 1 alpha square and so on, this is n. So the convolution of this with the input signal will actually give you the response, but it is also good to visualize it in the frequency domain. We can see what we can expect out of the signal, right? So if you have a DC signal, you can say that your amplitude is going to be boosted by 1 minus alpha. And if you have a very high frequency signal, you can say your amplitude is going to reduce by 1 plus alpha, right? So that is why these frequency response and filters are all useful. So it gives us another flexible way of looking at the signals and the systems. So this one was an example of a recursive filter. So we will see another example of a non-recursive filter. So non-recursive discrete time filters. So as a in general case, we can write y of n equal to summation. Let's say k equal to minus n to n, bk x of n minus k. And this needn't be n, it can be some other m. So your y of n is a weighted average of n plus m plus 1 values of x of n from x of n minus m through x of n plus n, correct? And what are the weights? It is given by bk. So averaging is usually performed to smoothen out the signal. To smooth out the signal. So if you are having very rapid variation, when you take an average, it is going to anyway smooth out the function, right? It is like integration. Okay. So let us take a simple example. So let's say your y of n is equal to average of x of n minus 1 plus x of n plus x of n plus 1. So the signal, the one before it and the one after it. So the impulse response of this will be 1 by 3 delta of n minus 1 plus delta of n plus delta of n plus 1. So from this I can find the frequency response, h of e power j omega, summation k equal to minus infinity to infinity, h of k e power minus j omega k. So this is going to be equal to 1 by 3. Delta of n minus 1 will give me e power j omega, plus delta of 0 will be e power j0, j omega 0, which is 1, plus e power minus j omega. So this and this I can combine. So it will give me 1 by 3 into 1 plus 2 cos omega. So this is my frequency response of this system, right? So how is my h of e power j omega going to look like? This is omega. Let's say this is pi and minus pi. Let me also plot pi by 2 and minus pi by 2. So at 0, this is going to be equal to 1. So 1 plus 2, 3. 1 by 3 will give me 1. At pi by 2, what happens? This term goes to 0. So I'll have 1 by 3. And at pi, this becomes minus 1, right? Cos omega becomes minus 1. So I'll have minus 1 by 3. Similarly, since cos omega is symmetric and 1 is also like a even function, we will have same relation on both sides. So how does it look? So it looks something like this, right? So if you want to stretch it, it will become something like this, correct? And if I just want to get the magnitude information, how will it look like? So I have pi by 2, pi, minus pi by 2, minus pi. So until sum, it will come like this, right? Close to pi by 2. And then again it is going to repeat like this. Something like this, right? So here it is 1. At here it is 1 by 3. 1 by 3. At pi it is again 1 by 3. So this is going to be equal. So you can say that it is going to completely remove the signal around this frequency, at this frequency. And it is actually boosting the signal at 1, and also it is somewhat suppressing the signal at pi, which is the high frequency component. So this is how you examine the filter response for the discrete time systems. So that's all for today. In the next video, let us solve some questions based on discrete time Fourier series. So until then, take care. Bye-bye.